Welcome to this Elevate 2025 presentation on integrating Python into PowerBuilder. In this presentation, we will go over why you might want to integrate Python into PowerBuilder, a couple of modern approaches for consuming Python libraries. We'll explore two of these approaches, one using Python.NET with a custom ad hoc wrapper and a library that I developed, and also through a web API, consuming it on PowerBuilder through PowerBuilder's REST client. I will then showcase a demo that makes use of these techniques, explain what they do, and how they do it. My name is Francisco Martinez. I am a tech support engineer at Appian, and I work mainly with C# development for applications and web APIs. My recent projects include the PowerBuilder Components app demo and the DW2Doc demo. Alright, for starters, why would we even want to integrate Python into PowerBuilder? Well, by accessing other environments' extensive ecosystem of libraries, we open up many possibilities for our applications, making them more versatile and powerful. Among the things that Python can provide are data transformation and analysis, machine learning and inference, natural language processing, and image document processing. By making use of these libraries, we no longer need to implement them ourselves in PowerBuilder, freeing our hands to focus rather on the UI and user experience. Here's a couple of approaches for using Python libraries from PowerBuilder. First, Python.NET, which is a .NET library that wraps Python on .NET. We then can make use of PowerBuilder's .NET assembly tool to interact with it. The second one would be to create a Python REST web API that provides the Python functionality as microservices. We can then consume these services in PowerBuilder through the REST client or HTTP client objects. First, let's take a look at Python.NET. This .NET library allows us to consume Python scripts using a custom C# wrapper through PowerBuilder's .NET assembly classes. And based on this library, we can follow three different approaches. The first and most basic one is to create a custom wrapper class that exposes only the functionality we need from the Python library, offering an interface that can then be consumed from PowerBuilder and implementing it on top of Python.NET. This approach is highly flexible because we can do things exactly how we need, only constrained by the data types that can be sent through the methods. It also offers the most freedom in terms of debugging because we know how we're implementing the code, and it's also the most high-performance approach of the three because there's a single layer of abstraction between PowerBuilder and the Python runtime. Now, the disadvantages of this approach is that we need robust C# knowledge or someone on the team who does, and also we will need time for developing the C# library. The wrapper C# library can then be imported into PowerBuilder with the .NET Importer tool. In case you're not familiar with this tool, we have a video explaining how to use it right here. The second approach is using the PyPb library. PyPb is a micro-framework that I developed as a solution for calling Python code from PowerBuilder. It aims to help PowerBuilder developers work with Python scripts without having to leave the IDE in a contained, concise, maintainable, and reusable way. It provides PowerBuilder objects that directly map to the corresponding C# classes, making it easy for PowerBuilder developers to work with it. It handles the mapping of data types between PowerBuilder and Python.NET, and additionally, it analyzes the Python objects and dynamically constructs C# objects with the same methods, making them so that they can be called straight from PowerBuilder. However, this approach is more verbose, as you need to set up invocation request objects, check for errors after every call, and depending on the approach, you will not be able to benefit from Python functions arguments with default values. This is the structure of the PyPb library. It acts like a bridge, with modules on both the Pb and C# side that interact with each other to provide functionality to access the Python.NET package in a Pb-compatible way. Python.NET then is the one who interfaces with Python runtime on the machine, executing the files we pass to it. Using this library is very simple. We first need to initialize the Python context by passing the path to a valid Python runtime DLL. There is also an alternative for leaving the library the task of downloading the runtime itself. Next, we open a Python file with the load module function, and once we have the module loaded correctly, we can interact with it. To call functions in the module, we can do so in 3 different ways. If the function does not take arguments, or it can be called without explicit arguments, we can use the invoke function on the module object directly. All functions in the library return an integer with a status code and pass the resulting object as a reference argument, as well as an error in case one occurs. If the function takes arguments, we can either create an invocation request object, configure the arguments values through it, and then call the invoke function, or make use of the dynamic functions that are generated on the .NET objects whenever a Python object is returned from any module or function. These proxy functions have the same name and signature as the source Python function, with the addition of the result returning and error passing arguments at the end. Please note that these proxy functions are generated on the .NET object itself, so both the result and the error need to have explicitly indicated the ref keyword. For class instantiation, the same last 2 methods can be used. We can think of it as invoking the classes constructors. For accessing an object's properties, we can use the get and set functions on the PyPb object NVO, and if for some reason you need to read the Python script's output, you can use the register for console output function to register a callback event. The objects in the PowerBuilder library are direct stand-ins for the essential C# classes, which allows the C# library to be used to the fullest. Now here are some recommendations for working with the Python libraries. If the library you want to use is very complex, it might be better to create a Python wrapper that exposes only the functionality you need, with simpler classes or functions with less complex signatures. Using the PyPb library can result in very verbose code, so you can consider using a custom-made C# wrapper around the Python functionality that you will need. And as for performance, if you're planning on running heavy tasks in Python, keep in mind that by default all operations run in the UI thread. Thus, you should consider moving these tasks onto a background thread to prevent the UI from locking up. And for tasks that are very computationally heavy, it's probably better to offload them to a dedicated microservice with more appropriate resources. When deploying an application that makes use of the PyPb library, it's necessary to have a Python runtime on the client machine. However, asking the user to install a dependency might not lead to the best results due to any combination of reasons. So here's a couple of ways to make Python available to the application without requiring the user to do absolutely anything. Python provides a light, minimal runtime that we can use in our projects. We're going to show this in the demo, but here's a summary of the steps. Download the 32-bit embeddable package. If you're working with a 64-bit app, you will need to recompile the PyPb binaries for 64-bit architecture and download the 64-bit Python runtime. Initially, I had tried to compile with the any CPU setting, but I found that this made the Python engine unable to run, so it's important to pay attention to this. Anyway, once you obtain the embeddable package for the appropriate CPU architecture, extract it onto a location inside the executables folder. Use this relative path as the Python DLL for initializing the context in the application. Use the piprex package to generate the dependencies file for the Python libraries we're using. And then finally install these dependencies onto the runtime location using pip install with the switch T. Alternatively, we can also make use of the python.included.NET library. it downloads the Python runtime onto the user's local files without needing admin rights. By using this, we don't need to manually provide a runtime, and it even has the ability of installing Python dependencies, but this means that we will need to know them beforehand. Now let's take a look at how to consume Python from PowerBuilder. This is the application I'll be using. It has a couple of examples of using Python to accomplish some simple tasks, and the one we will be focusing on is an extremely basic report-making app that can export a list of employees as an Excel file with pre-configured themes. For this example, let's make the following assumption. We need to generate those XLSX files with styles and charts, but we must not rely on Excel, nor we could find an appropriate PowerBuilder library that does this. Under these conditions, I found something that can help us with our requirements and is simple to use: a Python library called OpenPyXL. By taking a look at its documentation, we can see that creating a workbook is super easy, and writing to it takes nothing more than a couple of lines. This is the perfect tool for the work. But because it's made for Python, I need a way to use it from PowerBuilder. And that's exactly what we'll be seeing in this demo. I'm gonna demonstrate 3 different approaches to using Python from PowerBuilder to perform this, starting from the most simple one: creating a custom C# wrapper that does all the Python operation and just offers a basic interface to use it. This one has an additional feature for exporting a chart, which I'll be showing how to implement in Python. Let's first explore the C# solution that provides the function to the application. The Appian OpenPyXL wrapper project is composed of only 4 classes: the theme class, which defines a theme's parameters as an object, the XLSX writer object, which is the one that does the actual operations with the XLSX file, and the XLSX writer builder, with which we can build instances of the XLSX writer through a PB-friendly interface, and also a helper class named ArrayExtensions. Let's begin from the builder class. In here, I'll initialize the Python runtime by making use of the python.included package to install the Python runtime and its dependencies onto the client machine without having to worry about that myself. With this line, I initialize the python.net runtime. I need to do this before using any of the other library subjects. Then, before executing any set of Python actions, I must get a hold of the global interpreter lock. This lock will be disposed of when the method body exits, so I have to acquire it every time I want to do anything with Python. You will be seeing this statement in every method in which I do any Python operations. Immediately after that, I begin working with the Python runtime by importing the OpenPyXL module, then creating a workbook, access its active worksheet, and finally create an XLSX writer instance and return it. Inside the XLSX writer class, we have only a couple of methods. setTheme, with which we build the style objects that will be used when writing the data. We can see that we perform a very similar process here. We import the module we will use, then use python.net to execute Python statements to build the objects and pass them back to the C# runtime. We repeat this for the rest of the theme components. Next, the AutoSize method will go over all the cells in the spreadsheets and recalculate the column's width to fit the entire content. The save method is pretty straightforward. The write chart function, in which I'll be writing the chart, starts by importing the necessary packages from the runtime. I'll create a new sheet to put the data into, write the headers of the data table, Here I'm using the helper extension that I wrote that converts an array of any type into a PyList object. Next, I convert the decimal value into the Python's decimal type and write the data point into the table, repeating this for all data points. Next, I create a pie chart, create the references for the labels and the data, store these onto the locals dictionary, and then invoke the appropriate functions for the chart. At last, I invoke the addChart function in the worksheet. Lastly, let's look at the writeRow method. This method will be called for each row that we want to append onto the worksheet, so the writer has an internal state for the last written to row. To write the row, all we do is set up the locals, including the spreadsheet, row, column, style, some auxiliary variables, and then execute the Python code block, including these locals, into the execution. Now I'll export the library as a DLL to use in PowerBuilder. I'll select our project's location, x86 architecture, and now in PowerBuilder, I'll import our library by opening the .NET Assembly Importer tool. I'll select our DLL and select the builder and theme classes. Due to how it's built, we cannot directly import the XLSX writer class, which is the entire reason why we're using a separate builder class in the first place. Instead, I'll implement this NVO manually, after I finish importing these two classes. I will create a new NVO named end_cst XLSX writer and define init, a member of type .NET object, which will hold the .NET entity that backs it up. I'll also define functions with the same signatures as the C# object. These functions will simply forward the execution to the backing .NET object. And I'll do the same thing for all the other functions in the C# object. Lastly, I'll modify the builder NVO's build function to instead return an instance of our NVO that is wrapping the .NET object. I have also created beforehand a function that quickly converts a theme definition structure into a theme.NET object for use in our library. And with this, we have successfully imported our wrapper library into PowerBuilder. Now all we have to do is implement it in our application. In the writeData2XLSX static function, I will first declare our local variables, including the names of the data window objects from which I'll be obtaining the text values. Then create an instance of the XLSX writer builder, read the selected theme, load the theme configuration from our INI file where they're defined. I'll build the writer, set the theme, send the column headers to the worksheet, and then I loop over the data windows rows, and one by one I write them into the XLSX file. After writing everything, I adjust the column widths, invoke the writeChart function when configured, and finally save the XLSX file to the provided path. We can appreciate how simple and straightforward doing it like this is. By creating a custom wrapper, we can provide interfaces that require the exact amount of data to do what we need, and nothing else. I'll make sure that the code is configured to use this strategy and run the project. Great, we successfully created an XLSX file with Python from PowerBuilder. We achieved this by manually creating a wrapper C# library that fits our needs to a T. But what to do if our team doesn't have someone knowledgeable on C#? In that case, the next approach might be a better option. These next couple of strategies will revolve around the library that I wrote that will be provided in the session files, which aims to provide Python interoperability on PowerBuilder by using C# objects as an abstraction layer between them. This library, which I named PyPb, is composed of the objects inside the pypb-lib library in PowerBuilder and the binaries in the bin.pypb.appian directory. By the way, the source code for this library will also be available on the session files. To begin, I'll show you where the Python context, which is what all the components in the library depend on, is initialized in this app. Here on the Python runtime select window, which allows me to select a Python runtime I want to use, it will also detect if there's already a runtime in the project files and automatically use that, so that instead of showing itself, it will go straight into the main window. I'll open the Initialize buttons clicked event. In here, a quick validation of the selected runtime speedness is performed, and then the of_init context function is called, which in turn calls the pypb context init function. This function is part of the pypb-lib library, and it quickly instantiates a pypb context class on a single line. This context is required by all the objects in the library, so that's why it's the first thing that we need to create. After doing it, it's kept as an instance variable and then passed to the main window, which in turn assigns it to each one of the example user objects. Now back in the Excel writer example, I'll go to the export buttons clicked event and swap the function that will be doing the exporting. Instead of using our custom wrapper from the previous example, we'll use this other function. I'll be writing it and explaining it as I go. I'll begin by declaring our variables. The pypb module represents the Python file or package that we load. I'll need a pypb object for holding the workbook I create, another one for holding the method calls result, and an invocation request. As a reminder, these objects encapsulate a call to a function, method, or class constructor. I'll also have a string and an int for error handling. First, I'll load the OpenPyXL package through the pypb context that the main window passed to this object. Then, pretty much after every call to the library's object, there's gonna be some error checking, so we better get used to seeing this pattern here. Then, inside a try-catch block, I will create an instance of the invocation request targeting a workbook entity. These invocation request objects can be conveniently obtained from modules or objects and their independent entities. In this case, we don't need to configure any parameters, so we're just gonna use it like this by calling the instantiate function on the module. On library functions that return values, the result will be passed through the second to last parameter. Once the workbook has been successfully constructed, I will write all data into it. Then, after all the data is written to the workbook, I will create a new invocation request for the save function, configure its one argument, the path, then invoke this function on the workbook object to save it onto the disk. I'll write the rest of the try-catch block. And now let's implement the write data to workbook function. Here too, I'll begin by declaring the locals that I will use. Also, since I'll be accessing the rows through the data window object's names, I'll put their names and the headers' names too inside arrays to be able to easily access them with data window syntax. Inside the try-catch block, I will load the styling module first. This module is a custom Python file that builds open PyXL named style objects that we will then use to configure the spreadsheet's theme based on the parameters we pass to it. Next, I will retrieve the active spreadsheet from the workbook by using the get method on the PyPb object NBO. Then, based on the selected theme, I will configure either the default style or the appropriate style theme by reading the theme information from the INI file. I configure an invocation request to the create style function of the styling module, fill it with the theme parameters, and evoke it. I repeat this procedure for the other components of the theme, such as the row and the interleaving color. Finally, the default style, in case no theme was specified. Now to write the headers. I'll create an invocation request to the cell function on the worksheet, iterating over the header data window objects. I'll configure it with the row, column, and texts, and then invoke it. Then set the style for the cell. We clear the arguments from the request and repeat this for all the header controls that we declared at the beginning. Notice how the invocation request can be reused. To write the data itself, I follow the same procedure. Iterate over all the rows in the data window, then over each column object, configuring the cell position, value, and evoking the request. The signature of the function that we're calling is described in the Open PyXL documentation, so you need to know the library that you're working with in order to use it. The style to set will depend on whether the row is even or odd. Now, after writing all the rows, I want to resize the columns to fit their contents, so I'll implement this in a separate function called AutoFitColumns. I'll show you the implementation of this function in a bit. But first, I'll finish writing the try-catch block, and with this, I can run the application. As you can see, using this approach is very flexible, and you can work directly, quotation marks, with the Python objects without having to write an entire C# wrapper. But it can also become very verbose very quickly. So to help alleviate this, I have also implemented a mechanism that makes the PyPb objects have methods generated at runtime, with the same name and signature as those in the Python object they represent. This allows us to call these functions directly without needing an invocation request, and I'm going to show that approach next. Let's return to the write data to XLX function. To use the dynamic methods, all I have to do is replace the invocation requests with the equivalent. These dynamic methods are generated on the underlying .NET object, thus to be able to invoke them, I have to do it on the IDN host member of the PyPb object or module. Here I'm creating a workbook. The disadvantage of this approach is that we must explicitly specify all the arguments in the function/constructor. That is, default arguments values do not work. Another thing to note here is that all the generated methods have two additional parameters. one for passing back the invocation's results to the caller, and another for the error in case there is one. Because these functions are on the .NET object, we must explicitly specify the ref keyword on these last two arguments. Additionally, because we're working with the .NET object, the object we get back is also a .NET object, not a PyPb object. This is why I have also written a function called wrapObject that wraps the .NET object inside a PyPb object. This will be done on pretty much all calls done this way. You might notice that there's not much of a difference in terms of code length, but keep in mind that this call does not take any arguments. We'll see this being significant in a second. I'll replace the current writeDataToWorkbook function with the one I've rewritten with dynamic methods. But before jumping into that function, I'll replace the save call first. Now let's move on to the writeDataToWorkbook proxy function. The code pretty much looks the same except for the places where we make calls to functions, like here and also here. Where we create the cell is where we can appreciate the largest difference. We can call the function in a single line instead of having to configure the invocation request on several lines. This approach is fully compatible with invocation requests. For example, here, we have to use different functions to retrieve the value from the data window. So it's more practical to use an invocation request using a conditional statement to determine which function to call and which value to add. The generation of these functions is performed automatically, and for every object that crosses the line between Python and PowerBuilder. Meaning that accessing a property, for example, that returns an object will have its functions generated. The same thing for return values or object instantiation. You don't have to do anything to get this working. The rest of the function looks the exact same. Now, as promised, let's look at the AutoFetColumns function. The worksheet has an iterator for the columns, so I'll access it and keep it in the lnvColumns variable. Then we iterate over all the values the object produces. We can get the iterator values by calling the next function on the object. In Python, iterators and generators work by signaling the end of the collection by throwing an exception that is caught by Python's for statement handler. But because we're not doing a for statement here, we will get the exception thrown, and the PyPblib will return this as an error. That's why any error produced by the call to the next function we will interpret as the collection having ended. We're using invoke directly because the next function does not take any arguments. Next, we'll get the first item of the column, and from that, the column letter. We will use this column letter to access the column dimensions dictionary later. From the column, we will get the number of cells it contains. The object returned is a PyPb object, not an int, so we need to convert it explicitly. Because Python does not have hard typing, the toInt function and all other conversion functions only try to convert the value, and provide a status code of -1 and an error if it couldn't. Proceeding here, we will loop over all the cells in the columns, get the cell, then get the value and convert it to a string, storing the length of the largest string. After looping across all the cells, we will add a small padding to it, get the column dimensions map from the worksheet, then use the column letter to get the column dimensions object, and set its width property to the max value we calculated. Because we're calling the function on the raw .NET object, we also need to pass the backing .NET object from our column letter wrapper. This is repeated for all the columns in the worksheet, and after this is done, that's it. You can probably imagine how much larger this code would be if we had to rely on the invocation request for every single call. Fortunately, we can mix these two approaches and use whichever one is most convenient for the circumstance at hand. Now, let's assume we finished developing our project that relies on Python, and we're ready to deploy it to our customers. We could make them install the Python runtime themselves, but we cannot be sure that we'll install the correct version or that they will know how to do it in the first place. We can install it as part of our installation sequence, but polluting the client PC with an entire SDK when they will not be using it might not be the best idea. I'm going to show you one solution to this problem: embedding the Python runtime and project dependencies inside the project. For this, we will need to have Python installed, so if you don't have it, you can go to the Python page and download it. With Python installed, this is what we'll do. First, we'll download the Python embeddable package from the Python page. Then I'll create a folder inside the project's directory named Python. And extract that embeddable package inside it. I will then configure the application to use the Python DLL located in there. Now, to install the dependencies, this is very easy. I'll open a console window on the project folder and install the piprex package with this command. After this package finishes installing, I'll run it, indicating the location of my Python files. This will generate a requirements.txt file inside the folder, containing the dependencies of my Python project. Next, I'll install these dependencies onto the location of the embeddable runtime with this command. If instead of working with Python files directly, I were using the PyPb library to load a package like I did for the OpenPyXL demo, I would have to install that package manually like this. With these steps, once the application loads the Python DLL on our local folder, all the dependencies will be available. Alternatively, you could also use the python.included.net package to provide the Python runtime and install the dependencies on the client machine, just like we did on our first example. Let's look at the second approach for providing access to Python libraries to PowerBuilder, through a Python REST API. By using this approach, the user no longer needs to have a Python on their machine, but instead the Python code is deployed onto a REST web API that exposes a standard, language-agnostic interface that PowerBuilder can then consume through the REST or HTTP client objects. Creating the web API is super simple with a library such as FastAPI. This is pretty much all the code we need to set up a web API. Then, to consume these web APIs from PowerBuilder, all we have to do is send the appropriate requests through the HTTP or REST client. This approach also has some things that need to be taken into consideration, however. Due to the REST HTTP architecture, the exposed services need to be stateless and the data transmission serializable. The server that hosts the web API needs to be scaled in accordance to the potential clients and the workload. We also need to keep in mind the size of the payload that will be sent through the internet, both upstream and downstream. And we cannot forget that some workloads might take a long time to complete, and REST requests need to complete almost immediately. This might require some additional architecture design on the server component. Let's take a look at our example application implemented on a web API. In the PyPb.server directory, we have the files that make up our Python Web API server. Let's open this directory in Visual Studio Code. First thing we have to do is configure the database connection, which is read from the .env file. The Python driver for the SQL server only supports connections through ODBC, and I already have one set up on my machine, so I will just provide the DSN here. The main entry point for the Web API is the xlsx service.py file. We can see that the Web API itself is very simple. I only defined a root endpoint to test if the Web API is alive, and the endpoint that renders and returns an xlsx file. This endpoint can receive the same options that we can configure on the application UI, the theme name, and interleaving. Upon receiving the request, the function that actually creates the xlsx file is called. This function performs pretty much the same operations as we did on PowerBuilder through PyPb, but this time natively on Python. We set up the themes, then write the headers. Next, the data is provided by the getData function, which is imported from the SQL Server service file. Here's where we load the connection string from the .env file and execute the query that retrieves the data. With the data now in memory, we write it into the worksheet, autofit the columns, and save the file locally to disk, returning the file's location. Back on the Web API, we take this file and return it as a file response. Note that here we schedule the deletion of this file when the response finishes being sent. And that's pretty much it on the Python side. Now on PowerBuilder, if we open the download button's clicked event and then follow through to the download xlsx function, we will see that consuming this Web API is very simple. I create an HTTP client instance, contact the root endpoint just to make sure that the Web API exists, build the request URL with the options specified in the UI, and because we don't know how large the returning data will be, we disable automatic data loading to download the data in chunks. Then send the request. I open a file for writing on stream mode and start reading chunk by chunk, writing them as they come, repeating until there is no more data left. And that's pretty much all we have to do. Now for running this part of the demo, we will return to the Python servers directory and open a terminal here. For running this, we will need a Python runtime installed, but also the fast API package. So let's proceed and install it with this command. After this command completes, start the Web API by running fast API with this other command. Now if we run the application again and this time click on the download button, we will see how the xlsx file is generated. We have successfully extracted the Python functionality onto its own entity, and now we don't have to worry about Python dependencies on the client machine. Not to mention that a server can be better equipped to handle heavy loads than a client machine. And that's it for this session. I hope the topics mentioned in this presentation can help you integrate Python into your own projects. The project files and source code that I used in this demo will be offered on the session files for your reference. I will be in the chat answering any questions you might have, so thanks for watching.
Now is Q&A time. Welcome to join our live Q&A Zoom meeting with the presenter. You'll find the Zoom meeting link at the top of the chat panel and also in the resources area below. Just click and join us live. You can enter the meeting from the Zoom app or your browser. Just type your name and click Join. You'll be in a waiting room until the meeting starts, and you'll join automatically once it begins. Now that you're in, you have 10 minutes to ask the presenter any questions about this session. Don't miss the chance.